With particularly an arithmetic series, there is a fantastic little shortcut that can save you tons of time. And because lots of sequences you come across in applications in mathematics, especially as you go higher, do often tend to be arithmetic in nature, this is a good time saver. All right, so here's a story we'll start with about this gentleman here. This is a German mathematician named Carl Friedrich Gauss, who was at one point a wee young lad. The story, I don't know if it's true or not, but it's a good story, was that the teacher that he had one day was trying to get some work done and wanted to keep the students busy. And so said, hey, kids, I need you to add up the numbers from 1 to 100, right? And then come to me when you've got the answer. And Carl Gauss came up in about 30 seconds or a minute and had the correct answer. And the teacher was positive he couldn't have done it that quickly because nobody can add that many numbers that fast. And of course, he was right. And he didn't actually add that many numbers that fast. He found a fantastic shortcut. And it's not even that hard to understand. So let's see what we got. Right now, let's imagine I don't know what this sum is. Okay, so I'm going to call it S. S for sum. I do know that the way you find the sum is you take 1 and add it to 2 and add it to 3 and add it to 4 and keep on adding. Too many dots there, just 3 dots, until you get all the way up to 97, 98, 99, and 100. So what many students did, and frankly probably what I would have done, just said, okay, 1 plus 2 is 3, add 3 is 6, add 4 is 10, add 5 is 15, and then just keep going on. That would take a while. Carl did this. He said, all right, well, if the sum is this, I could also write it this way, couldn't I? Couldn't I start with 100 and add the 99 and add the 98 and add the 97 all the way down to the 4 and the 3 and the 2 and the 1? I think we can buy that. Yeah, because if you're adding, you can add them in whatever order you want, end up in the same spot. He then said, well, wait a minute, I'm noticing something. What if I took these two expressions, these two equations, and added them together? Well, it would be what? S times S, or sorry, S plus S. That's 2 S's, so double the sum. 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98, is 101. And then this continues all the way through to the very end. When you set up, because of the arithmetic pattern, because we're going up by the same amount each time, and therefore the second line is coming down by the same amount each time, you get this exact same sum from start to finish. So he said, all right, so 2 times the sum, well, that's just 101 100 times. And then he said, but I don't want 2 times the sum. I want just that original sum. So divide by 2. And he then, not an S there, I want a 2. He then said, all right, well, I guess I'm there pretty quick then, because my sum is 100 divided by 2 times 101. That's 50 times 101, which is 5,050. And he got there, not immediately, but very, very quickly. Now, in general terms, here's what he did. He said, all right, I got this arithmetic sequence. I took the first term, which was the 1. I took the very last term. I'm going to call that AN, A sub n, which was 100 in this case. So 1 plus 100, that's the 101. And then he said, I had that n divided by 2 times. There were 100 numbers. But remember, we kind of used everyone twice to get these sums going on, so hence the division by 2. And this, my friends, is the formula we're going to use to calculate our arithmetic sequence, or arithmetic series sums. An incredibly brilliant insight. So I'm going to go back now here to this part of the toolkit, uncover this. There it is. The way you find the sum of an arithmetic series is the number of terms divided by 2. And then in parentheses, first term plus last term. We're going to take advantage of that Gauss shortcut. All right, so here's just a couple more. What is the sum of the even integers from 2 through 100. All right, if you think you know what to do, by all means, do a quick pause, give it a shot, see if you can come up with that answer. And then if you're less sure, we'll take a look at it here together. So first, I do want you to recognize this is an arithmetic series because you go from 2 to 4 to 6 to 8, all the way up to 100. And we're adding the same number each time. So by definition, this is an arithmetic series because we're adding 2 to get from term to term. So what is this sum? Well, we need to know a few things. I need to know, just in general, how many terms I have, what the first term is, and what the last term is. Now I'm going to use a little n down here just to show how many terms we're adding up. So that's what that number down there will mean, just so you're aware. So in this particular case, let's do some of the easier parts first. I know that my first term is 2. I know that my last term is 100. What you have to think about just a little bit is how many terms there are. And I hope it can convince you there's going to be 50. So we're adding up 50 numbers that follow that pattern. So the n to use is the number 50. So I'm going to pull up my handy calculator machine. 50 divided by 2, well, that's just 25. 2 plus 100, that's 102. So 25 times 102 ends up being a sum of 2,550. Just like that. Added up those 50 numbers super quick. Important to know, this shortcut works only if your series follows this arithmetic pattern. If to go from number to number, you're adding the same thing on each time. Okay, last one. I'm going to get a little more space. What is the sum of the first 1,000 multiples of 3? Ooh, well, here we go. Let's start with the sum of these 1,000 different numbers. So that's just a label, adding up the first 1,000. Number of terms divided by 2, that's always a 2. First term, well, the first multiple of 3 would be 3 times 1. Plus the last term. The 1,000th multiple of 3 would be 3 times 1,000. And just like this, we don't have to add up 1,000 different numbers. We're using our Gaussian shortcut to say, all right, 1,000 divided by 2, well, that's 500. 3 plus 3,000 is 3,003. Multiply those out. We end up with, 1,501,500. And just like that, we've got that series calculated. What I want to do next is, for those of us that are visual people, I'm a visual person, I want us to see kind of what this looks like in terms of actual geometry. So we're going to take a look here at 3 examples. If these are helpful for you, great. If they don't quite do it for you, then please just trust us. This formula does work. There is a pattern, there is a structure that we're taking advantage of. So here in this first case, my sequence is just a sub n equals n. So this would start with what if I put a 1 in for the n, I just get 1, and then 2, and then 3. This is just a way of describing the counting numbers. The sequence of counting numbers is just those numbers themselves. So 1, 2, 3, 4, 5, 6, 7. What we're going to examine is the sum of the first 7 terms of this sequence, which is the sum from n equals 1 to 7 of a sub n. So bringing that summation notation into it. Well, let's first of all see what the answer should be. We know that it's going to be the number of terms divided by 2 times the first term plus the last term. This ends up being 28 overall, yeah? So this sum is 28. What we did was basically add the heights of these different bars together multiplied by their widths. Essentially, it was an area calculation. What we do when we say, all right, I want to take 7 over 2 times 1 plus 7, we're saying take the lowest bar and the highest bar, add them up and divide by 2 to average them. That gives us a height here at, let me get my line maker, at a height of 3.5. That is the world's fattest line. All right, I need to make that line a little less fat. There we go. And something magic happens. If you take a look at, say, this bit that's above the line, well, that's the exact same size as this bit that's below the line. This part that's above the line fills in this part below the line. Exactly. This part above the line fills in this part below the line, and this above fills this below. What we're saying is, I'm going to now switch colors to a blue. Adding up the heights of all the bars, which takes some time and is a little bit cumbersome, is the same as finding the area of this rectangle, which is just a length of 7 times a width of 7 plus 1 divided by 2. 7 times 7 plus 1 divided by 2. So geometrically, this is a very fancy way of finding the area of a rectangle. The same thing is true even if you have negatives involved. It's just that we're going to consider negative area to actually kind of be a thing. That just means that it's area below the x-axis. So let's find the sum here, the first 12 terms of this sequence. Okay, well, I know for the sum of these 12 terms, I'm going to do number of terms divided by 2 times first term plus last term. Well, what are the first and last terms? For the first term, put a 1 in for the ends. 1 minus 1 is 0. 0 times a half is 0. Negative 2 minus 0 is negative 2. So that right here at that height of negative 2, that represents our first term in the sequence. Now for the last term, we're going to put a 12 in there. So a 12 minus 1 is 11. 11 times negative a half is negative 11 halves. Negative 2 minus 11 halves is negative 7.5. Does that look about right? So negative 5, 6, 7.5. Yep, sure enough. Negative 7.5 for the height of the last term of the sequence there. Throw this all into our calculator machine. And what we end up with is negative 57. So here's what we're saying. If you take basically this shape, so it's a trapezoid, and if you calculate the area of that trapezoid, you end up with a total accumulation, a negative area of negative 57. Now, just trust me, it gets a little more complicated geometrically when some of your results are positive and some are negative, but it works itself out. If you find it interesting at all that sometimes you can think of areas as negative, then make sure you take a calculus class because that's an important idea when you look at definite integration. Okay, let's do the same thing just for practice. Let's find now the sum of all of these little dot heights, so all the y coordinates of these points here. That'd be the sum of this series. So the first 20 terms of this arithmetic pattern. Let's first find, and I'm going to go up here just for space. I know it's going to be number of terms, and there are 20 of them, divided by 2. First term, put a 1 in here. 1 minus 1 is 0. 2 times 0 is 0. 3 minus 0 is 3. All right, so there's my first term at a height of 3. Now the last term, let's put a 20 in here. 20 minus 1, that's 19. 2 times 19 is 38. 3 minus 38 is negative 35. So 20, 35, sure enough, right there we are at a height of negative 35. Taking advantage of Karl Gauss's shortcut. So this is just 10 times negative 32 for a total of negative 320. So like I said, if you are looking for, if you like a geometric interpretation, we're essentially taking this sort of shape and making it rectangular. It's equivalent to finding the area of a trapezoid, and it kind of all balances out in the end. So that's where our Gauss shortcut gets us.